lie still for a moment, because all of this is already happening. 4 light-years from the bed you're lying in there is a star you have never seen, too faint for human eyes, with a rocky world going round it every 11 days. It is the nearest thing to a second Earth that physics has put within our reach. Here is what the journey there actually looks like. A spacecraft the mass of a paperclip crossing that planet's whole orbit in 4 minutes and then leaving forever because nothing aboard it can stop. A sail folded away behind a shield for 21 years because 1 grain of dust at that speed arrives like half a ton of high explosive. A child born in year 300 of a voyage who will never see a horizon. 98 people, the smallest crew the arithmetic will allow, and a stage in New York in 2016, $100 million, and a promise, then 9 years of silence. Tonight we walk the whole journey with an honest ledger, and by the end you will know exactly why, on every plan we have, they never arrive. Get comfortable. If you're the kind of person who would rather have the real number than the comfortable one, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the word arrive will not mean what you thought it meant. Now, let's gently drift into this. Go outside tonight, anywhere in the southern half of the world, and look toward the constellation Centaurus. There is a bright pair of stars there, one of the finest sights in that part of the sky, and almost every guidebook will tell you that you are looking at the nearest star system to our own. That much is true. What the guidebook usually leaves out is that the nearest star itself is not in that view at all. It is sitting about 2 degrees away from that bright pair, in a patch of sky that looks to your eye completely empty. You could stare at that exact spot for an hour on the clearest night of your life and never see it. To see the closest star to Earth, you need a telescope. That fact is the correct place to start because it sets the tone for everything that follows. Proxima Centauri is a red dwarf, and red dwarfs are the quiet majority of this galaxy. It carries about 12% of the mass of the Sun and roughly 14% of its radius, which makes it only a little larger than the planet Jupiter. Its surface sits at around 3000 Kelvin, about half the temperature of the Sun's, and it radiates most of its output in the infrared, in wavelengths your eye simply does not register. Add all of its light together, across every wavelength, and you get about 1/6 of 1% of the Sun's output. In visible light alone, it is far dimmer than that. Its apparent magnitude is about 11, which puts it roughly 100 times below the faintest star a healthy human eye can detect from a dark sight. Nobody knew it was there until the 20th century. In 1915, an astronomer named Robert Innes, working at the Union Observatory in Johannesburg, noticed a faint red point that was drifting across the sky at the same rate and in the same direction as the bright Alpha Centauri pair. 2 things moving together, at that rate, usually means 2 things travelling together. 2 years later, in 1917, Alexander Vogt measured the star's parallax, and the number came back closer than any star ever measured. It has held the title ever since. It will hold it for about another 25,000 years, drifting slowly closer until it reaches roughly 3 light-years from us, and then it will begin to move away again, and hand the title to something else. So we have a neighbour, and the neighbour is invisible, and it took the invention of the photographic plate for us to notice it at all. It gets stranger. Proxima is gravitationally bound to that bright pair you can see, but only barely, and only at a distance that is difficult to hold in the mind. It circles Alpha Centauri A and B at roughly 13,000 times the distance from the Earth to the Sun, taking somewhere in the region of 500,000 years to complete a single orbit. That orbit is so slow and so wide that astronomers argued for decades about whether Proxima was truly part of the system or simply a star passing through the neighbourhood at a similar speed. The question was only settled in the last decade, once the radial velocity measurements became precise enough to catch the faint pull. It is a member of the family, but it is the kind of family member who lives 4,000 miles away and visits once a geological era. Now the distance itself, because the distance is the entire subject of this video, and it deserves to be stated properly rather than waved at. Proxima Centauri is 4.24 light-years from Earth. That is about 40 trillion kilometres. Written out in units you might actually use, it is roughly 268,000 times the distance from here to the Sun. Light, which is the fastest thing that exists and which does not need to carry fuel or slow down or worry about anything, takes 4 years and about 3 months to make the crossing. That means if you were standing on a planet at Proxima right now, and you sent a radio message to Earth asking a simple question, and someone here answered it the instant it arrived, you would wait 8.5 years for the reply. A conversation of 10 exchanges would take longer than most careers. Numbers at that size stop meaning anything, so here is a model instead. Take the sun and shrink it down to a grain of sand, 1 millimeter across, and put it on a table in front of you. On that scale, the Earth is an almost invisible speck of dust about 11 centimeters away. You could cover the entire orbit with your hand. Neptune, the outermost planet, is a smaller speck 3 1/3 meters out, across the room. The 2 Voyager spacecraft, the most distant objects our species has ever made, are somewhere out around 18 and 15 meters, near the far wall. And Proxima Centauri, the nearest star, the neighbor, the destination, is another grain of sand 29 kilometers away. Not 29 meters, 29 kilometers. On the scale where the entire solar system fits in a large room, the nearest star is in the next city, and every single thing between those 2 grains of sand is nothing. 40 trillion kilometers of nothing. Hold on to that phrase, because it is going to change meaning twice before we are done. Here is why anyone bothers. In August of 2016, a campaign called Pale Red Dot announced that they had found a planet there. Not a gas giant, not a scorched cinder, but a rocky world with a minimum mass of about 1.07 times the Earth's, orbiting Proxima once every 11.2 days at a distance of just under 5% of the Earth-Sun gap. That sounds impossibly close, and by the standards of our own system it is. It would fit comfortably inside the orbit of Mercury 8 times over. But Proxima is so faint that this tight little orbit puts the planet squarely inside what astronomers call the habitable zone, the band around a star where the temperature would allow liquid water to sit on a surface without boiling away or freezing solid. The nearest star to the Sun has a roughly Earth-sized planet in its habitable zone. That sentence is the reason this entire field of study exists. There is more there than just that one world. In 2022, using an instrument called Espresso on the Very Large Telescope in Chile, a team confirmed a second planet, Proxima d, with a mass of only about a quarter of Earth's and an orbit of just over 5 days. At the time, it was the lightest planet ever weighed by that method. The wobble it produces in its star amounts to about 40 centimeters per second, which is to say that astronomers in Chile detected a star shifting toward and away from us, at roughly walking pace, from 4 light-years off. A third candidate, sometimes called Proxima c, with an orbit of about 5 years, remains disputed and unconfirmed. So the destination is real, it is specific, it has an address and a mass and an orbital period we can quote to 3 decimal places, and it is closer than anything else will ever be. Every serious interstellar mission concept ever drawn, and there have been several, drawn by very serious people with very sharp pencils, points at this system. When you hear someone say that humanity should become an interstellar species, this is the place they mean. There is no second option. Everything else is further, which brings us to the question, and I want to pose it as precisely as I can, because the precision is where this gets interesting. Not, could we go? Not, will we go? Those questions get answered in slogans. The question is, what would actually happen? If you built the thing, and you launched it, and you followed it the whole way with a stopwatch and an honest ledger, what happens? What happens in year 1, in year 20, in year 300? What does the ship look like when it gets there? Who is aboard it? What do they find? I have spent a long time going through the arithmetic on this, and I want to be straight with you about where it goes, because it is not where I expected. The obstacle is not the one everyone talks about. It is not that the distance is too great. The distance turns out to be crossable, at least on paper, and more than one design would do it. It is not that we lack the physics. Every barrier in this video is legal under the laws of the universe. The problem is something else, and it shows up 11 separate times, in 11 completely unrelated places, wearing a different face each time. Every plan works. Every plan gets something to Proxima Centauri. And in every single case, when you follow the ledger all the way to the last line, the thing that arrives is not the thing that left. By the end of tonight you will know exactly why, and you will know it well enough to explain it to somebody else. But we have to build up to it, because if I told you now it would sound like a slogan, and this deserves better than that. Let us start with the honest baseline. Before we design anything, before we spend anything, before we imagine anything, what can we actually do right now, tonight, with the machines that already exist and are already moving? There is a machine about 25 billion kilometers from here, moving away from the Sun at roughly 17 kilometers every second, and it has been doing that continuously since September of 1977. It weighs about 720 kilograms. Its radio transmitter puts out 23 watts, which is less power than the bulb in a reading lamp. Its onboard memory holds about 70 kilobytes, which is smaller than a single photograph taken on a modern phone. It is called Voyager 1, and it is the fastest, furthest, longest-serving object our species has ever put into the sky. Voyager 2 actually left first, on the 20th of August 1977. Voyager 1 followed 16 days later, on the 5th of September, and overtook its twin because it flew a shorter and more aggressive route past Jupiter and Saturn. Voyager 2 took the long way around and became the only spacecraft in history to visit Uranus in January of 1986, and Neptune in August of 1989. Voyager 1 crossed the heliopause, the boundary where the Sun's outward wind finally loses to the wind between the stars, in August of 2012 at about 121 times the Earth-Sun distance. Voyager 2 crossed 6 years later, in November of 2018. Both of them are now, by the strict definition, in interstellar space. And here is what that has brought us. It is worth pausing on how fast 17 kilometers per second actually is, because in every human frame of reference it is enormous. A rifle bullet leaves the barrel at somewhere around 1 kilometer per second. The International Space Station, which is fast enough to circle the entire planet every 90 minutes, manages 7.66. Voyager 1 is moving at more than twice the speed of the fastest thing in orbit around the Earth, and about 17 times the speed of a bullet, and it has been doing it without pause, without a course correction, without slowing by any measurable amount, for longer than most people watching this have been alive. The signal it sends now takes more than 22 hours to reach us, which means the antennas on Earth are listening to a message that left the craft yesterday. This is not a slow machine. This is the fastest thing we have. In 49 years of continuous flight, at 61,000 kilometers per hour, Voyager 1 has covered roughly 2.7 thousandths of a light year. Proxima Centauri is 4.24 light years away. If Voyager 1 were pointed at Proxima, which it is not, it would need about 75,000 years to get there. Let that number settle for a moment, because it deserves a comparison rather than a reaction. 75,000 years ago, anatomically modern humans were still confined almost entirely to Africa. The Neanderthals had not yet met us. There was no agriculture, no writing, no wheel, no fired pottery. Everything you would call human history occupies the last 4% of that interval. If a Voyager had launched at the beginning of that span carrying a crew, it would be arriving at Proxima Centauri roughly now, and the descendants aboard would have spent longer inside the ship than our entire species has spent building civilization. Put differently, in half a century of flight, Voyager 1 has crossed about 0.06% of the way to the nearest star. Let me take you out there for a second, because the number does not land the way the picture does. You are matching velocity with it. There is no sensation of speed, because there is nothing nearby to move past. The stars ahead are exactly where they were when it launched, and they will still be there when it stops transmitting. The Sun is behind you, and it is bright, but it is a star now rather than a source of daylight. It casts a light too weak to read by. The craft itself is a lopsided assembly of struts and dishes and booms, its high-gain antenna aimed permanently back at a planet it can no longer resolve. Bolted to one side is a gold-plated copper disc containing greetings in 55 languages, whale song, a Bach prelude, and a photograph of a woman eating grapes. Its plutonium generators are losing about 4 watts of output every year, and by the end of this decade there will not be enough power left to run a single instrument. It will keep flying at exactly the same speed, in exactly the same direction, silent, for the next 75,000 years, and it will not arrive anywhere, because it was never aimed anywhere. The closest it comes to any star at all is a red dwarf called Gliese 445, which it will pass at a distance of about 1.5 light years in roughly 40,000 years, long after everyone who worked on it is forgotten. That is our fastest ambassador. Now here is our fastest launch. New Horizons left Earth on the 19th of January 2006 at about 58,500 kilometers per hour, the highest launch velocity ever achieved by a human vehicle. It reached Pluto in 9.5 years, which is genuinely fast for that distance, and yet today it is receding at about 16.3 kilometers per second, which is slower than Voyager 1. The reason is instructive. Voyager 1 did not get its speed from its rocket. It got it by stealing angular momentum from Jupiter and Saturn on the way past, in a maneuver we call a gravity assist, and it stole more of it than New Horizons managed to take from Jupiter alone. The launch vehicle is almost a footnote. Nearly all the velocity in interstellar flight so far has been borrowed from planets. That borrowing was itself a piece of luck rather than a capability. The Voyager route depended on an alignment of Jupiter, Saturn, Uranus and Neptune that occurs roughly once every 175 years, spotted by a young engineer named Gary Flandreau at the Jet Propulsion Laboratory in 1965. He was calculating trajectories to the outer planets and noticed that the giants were about to line up in a way that would let a single small craft be flung from one to the next, like a stone skipped across water. Miss that window, and you wait until the 2150s. So the two fastest objects our species has ever released were fast, because 4 planets happened to be standing in the right places during the decade we finally had the electronics to take advantage of it. We did not build that speed. We found it lying on the ground and picked it up. The outright speed record belongs to something else entirely. On the 24th of December, 2024, the Parker Solar Probe passed within a few million kilometers of the Sun's surface and hit 192.2 kilometers per second, about 692,000 kilometers per hour. That is the fastest any human-built object has ever moved. It is also 0.064% of the speed of light, and it does not count, which is the part that matters. That speed is not a cruise velocity. It is the speed of an object falling into a gravity well, and gravity wells charge admission on the way out. Parker gave every meter per second of it back as it climbed away from the Sun. If you could somehow bottle that number and hold it steady all the way to Proxima, the transit would take about 6,600 years. Better than 75,000 certainly, but still a journey during which every language spoken at launch would go extinct several times over. For crewed flight, the picture is worse, and it is worse in a way that surprises people. The fastest humans have ever travelled is about 39,900 kilometers per hour, achieved by the crew of Apollo 10 during their return from lunar orbit in May of 1969. That record is now 57 years old. Nothing has come close since. The furthest any human has ever been from Earth was set in April of 1970 by the crew of Apollo 13 swinging around the far side of the Moon. We have not been back. Every human being alive today, with the exception of a handful of orbital crews, is closer to the centre of the Earth than the distance between London and Sydney. Add up everything our species has ever sent out of the solar system, and the list is 5 objects. Pioneer 10, Pioneer 11, the 2 Voyagers, and New Horizons. Their combined mass is under 3 tons. Contact with Pioneer 11 was lost in 1995, and with Pioneer 10 in 2003. 3 of the 5 are already dead. The total physical export of human civilization in the entire history of human civilization weighs less than a car, and most of it is no longer answering. So there is an answer to the question, and it arrives early, and it is flat. Can we get to Proxima Centauri? No, not with what we have. What we have is 75,000 years and a set of instruments that will be silent for 74,950 of them. Except that answer is a trick, and I want to be honest about why. None of those 5 machines was designed to go to a star. Not one. Voyager was built to photograph the outer planets during a rare alignment, and then keep going because there was nothing else to do with it. New Horizons was built for Pluto. Parker was built to fly into the Sun's atmosphere. Asking those vehicles to reach Proxima is like asking why a fishing boat has not crossed the Pacific. The answer is not that boats cannot cross the Pacific. The real question is not what our accidental leftovers can do. It is what a machine designed from scratch for this single purpose could do. And humanity has designed those machines, repeatedly, in detail, with named engineers and published mass budgets and specified fuel loads. So before we look at what those designs promise, we have to look at what they are up against, and it is not the distance. It is a piece of mathematics written down in 1903 by a Russian schoolteacher in a paper almost nobody read at the time. In a wooden house in the Russian town of Kaluga, a provincial schoolteacher who had been almost completely deaf since a childhood bout of scarlet fever spent his evenings filling notebooks with equations about spaceflight. His name was Konstantin Tsiolkovsky. He taught arithmetic to village children by day, He had never seen a rocket capable of leaving the ground because none existed. In 1903, the same year the Wright brothers got a powered aircraft into the air for 12 seconds, Tsiolkovsky published a paper containing the single most important sentence ever written about interstellar travel, and almost nobody read it. The sentence, in modern terms, says this: the change in speed a rocket can achieve equals the speed of its exhaust, multiplied by the natural logarithm of the ratio between its starting mass and its ending mass. That looks harmless. It is not. Everything difficult about leaving this solar system is hiding inside that logarithm. Here is what it means in practice. A rocket goes faster by throwing mass backwards. The faster it throws that mass, the more speed it gets per kilogram thrown. That is the exhaust velocity term, and it is a straightforward multiplier. But the amount of speed you get from carrying more fuel does not rise in a straight line. It rises as a logarithm, which is the slowest growing useful function in mathematics. Turn it around and you get the version that ruins everything. To gain a fixed amount of extra speed, you do not add a fixed amount of fuel. You multiply the fuel you already had. Want to go twice as fast? You do not double the fuel. You square the mass ratio. Want to go 3 times as fast? You cube it. You can see this without any equations at all by looking at a Saturn V on the pad. That vehicle stood 111 meters tall and weighed about 2,970 tons at ignition. Of that, roughly 45 tons actually went to the moon. Everything else, over 98% of the machine, was fuel, or tankage to hold fuel, or engines to burn fuel, all of it discarded along the way. That was the price of a change in velocity of about 16 kilometers per second. And Apollo is the most efficient large chemical mission ever flown. Put numbers on the doubling and the trap becomes obvious. Suppose a rocket needs a mass ratio of 20 to reach some speed. 20 kilograms on the pad for every 1 kilogram that arrives, which is roughly a realistic figure for reaching Earth orbit. To reach twice that speed with the same engine, the mass ratio is not 40. It is 400. 4 times that speed needs a mass ratio of 160,000. 8 times needs 25 billion. The curve does not bend gently. It turns and goes vertical, and it does so within the first few doublings. Every engineer who has ever worked on launch vehicles has spent their career fighting this single relationship, which is why launch mass fractions have barely improved in 60 years, despite everything else about the technology being unrecognizable. There are ways to cheat at the margins, and we already use all of them. Staging, throwing away empty tanks so you stop paying to accelerate them, is the reason multi-stage rockets exist at all. Gravity assists borrow momentum from planets. The Oberth effect lets you burn fuel far down inside a gravity well where each kilogram of propellant buys more energy. These are real, and they matter, and together they are the difference between reaching Pluto in 9 years and never reaching it. But every one of them buys you a small multiple. None of them touches the exponent. You cannot out-clever a logarithm, you can only pay it. Now apply the same arithmetic to a star. Chemical rockets are limited by chemistry. The best practical propellant combination we have, liquid hydrogen and liquid oxygen, produces an exhaust velocity of around 4.4 kilometers per second, and that ceiling is set by the energy released when hydrogen and oxygen bond, which is a property of the electron shells of 2 specific atoms and is not subject to negotiation. Suppose you wanted to reach 1% of the speed of light, 3,000 kilometers per second, which would still take 425 years to reach Proxima. Feed those numbers into Tsiolkovsky's equation, and the required mass ratio comes out as a number with hundreds of digits in it. Not hundreds of tons, hundreds of digits. There is not that much matter in the observable universe. You could convert every atom in every galaxy we can see into rocket fuel, and you would not have enough to push a single chemical rocket to 1% of light speed. This is not an exaggeration for effect. It is what the equation returns. Chemical propulsion is not slow for interstellar purposes. It is disqualified. So set fuel aside for a moment and look at raw energy instead, because that gives you the shape of the wall without any assumptions about how the engine works. To move a mass at speed, you have to give it kinetic energy. To push 1 kilogram, a bag of sugar, to 10% of the speed of light requires about 4.5 times 10 to the 14th joules. In more familiar units, that is roughly 100 kilotons of TNT. It is about 5 Hiroshimas per kilogram, and that is the theoretical minimum, assuming a perfect engine with no losses whatsoever, which does not exist and cannot exist. Scale it to something you might actually want to send. A 1,000-ton vessel, smaller than a cruise ship, roughly the mass of a fully loaded jumbo jet and its fuel. pushed to a tenth of light speed, carries about 4.5 times 10 to the 20th joules of kinetic energy. Global primary energy consumption across every power station, every engine, every furnace, every vehicle on this planet is around 6 times 10 to the 20th joules per year. So the energy bill for accelerating 1,000-ton ship to a tenth of the speed of light is roughly 3/4 of everything human civilization burns in a year. All of it delivered to one object at perfect efficiency, with nothing lost as heat, and with no allowance whatsoever for slowing down at the other end, which, as we'll see, costs about the same again. I want to stop here, because this is the moment the shape of the problem changes, and it is easy to slide past it. You have spent your whole life inside a story that says difficulty yields to effort. Build a better engine, find a lighter material, fund it properly, wait for the technology. That story is true almost everywhere, and it is the reason human beings are good at things. It does not apply here, and the reason it does not apply is unusually clean. This is not a shortage. Nobody is withholding anything. There is no invention pending, no breakthrough overdue, no committee sitting on the answer. It is a ratio, and a ratio of that size does not care how badly you want the outcome, how clever your engineers are, or how much money you put behind it. Squaring an impossible number does not give you a merely difficult one. It gives you a worse impossible number. Every advocate for interstellar flight at some point reaches for the same comparison. The caravel, the wooden ship, the ocean that looked infinite until somebody sailed across it. It is a comforting comparison, and it is the single most misleading idea in this entire field. The Atlantic did not require more energy than Europe possessed. Crossing it required courage, provisions, and a willingness to be wrong about the shape of the world. Crossing to Proxima requires an amount of energy comparable to a planetary civilization's annual output delivered to a single object. Those are not the same kind of problem, and calling them the same kind of problem has probably done more damage to clear thinking about this subject than any other single sentence. Which raises the obvious question. If chemistry is disqualified, what has more energy in it? There is a ladder here, and it is short. Burning chemical fuel converts about 1/10,000,000th of the fuel's rest mass into usable energy. Splitting uranium nuclei converts about 1 part in 1,000. Fusing hydrogen isotopes converts around 4 parts in 1,000. And annihilating matter with antimatter converts 100%. Every gram of antimatter meeting a gram of ordinary matter releases about 1.8 times 10 to the 14th joules, the equivalent of roughly 43 kilotons of TNT, from 2 grams of material you could balance on a fingertip. Antimatter is the perfect fuel, and here is what it costs. The particle accelerators at CERN and elsewhere produce antiprotons at a rate measured in nanograms per year. At current production rates and costs, a single gram of antimatter would cost somewhere in the region of $1 quadrillion, and take longer than the age of civilization to accumulate. Storing it is worse, because antimatter annihilates on contact with anything, including the walls of its container, so it must be held in a magnetic trap in a vacuum better than interstellar space, indefinitely, without a single power interruption. So the ladder goes, chemistry is disqualified, fission is barely adequate, fusion is genuinely promising, and antimatter is a physicist's answer rather than an engineer's, which leaves fusion. And that is exactly where the serious designs went, not in the future, not in a laboratory, but in the 1950s and 1970s, on drawing boards, by people who calculated the whole thing to 4 significant figures and then found out what happens when you actually try to get a starship funded. On the 27th of August, 1957, at a test site in the Nevada desert, a 4-inch thick steel plate was welded over the top of a vertical shaft with a small nuclear device at the bottom of it. The plate was there to cap the shaft. It was not an experiment. When the device fired, a high-speed camera looking at the wellhead caught the plate in exactly 1 frame, and then it was gone. The physicist who ran the calculation afterwards, Robert Brownlee, worked out that the plate had left at something like 66 kilometers per second, roughly 6 times the escape velocity of the Earth. He was careful, then and later, to say that the plate almost certainly burned up in the atmosphere on the way out, and that his own estimate was a rough one. But the number is real, and the number is 4 times faster than Voyager 1. A nuclear explosion, it turns out, is very good at moving heavy objects extremely quickly, and there were people in 1957 who noticed. Project Orion began the following year at General Atomics in La Jolla, California, and ran until 1963. Its central figures were Ted Taylor, a bomb designer who had grown uneasy about bombs, and Freeman Dyson, one of the finest theoretical physicists of the century, who took a leave of absence from Princeton to work on it because he thought it was the most important thing anyone was doing. The concept was almost absurdly direct. You build a very large, very strong steel plate, you attach it to the back of a spacecraft with enormous shock absorbers, and then you drop small, precisely shaped nuclear charges out of the back, one after another, and detonate each one a short distance behind the plate. Each detonation slams the plate forward. The shock absorbers turn the hammer blow into a push. You do this a few thousand times, at roughly 1 detonation per second, and you leave. The plate would be sprayed with a thin film of oil between pulses to protect it from ablation, and calculations suggested that its surface would survive because the pulses were so short that the heat had no time to penetrate. There was a chemical explosive test vehicle, nicknamed Putt-Putt, which flew successfully in November of 1959 using conventional charges, a 1-metre model that rose about 30 metres on a stack of small explosions and landed intact, proving that the pulse principle worked and that the vehicle could be stabilised. Orion is the only interstellar-capable propulsion system ever proposed for which every single component already existed. Not a projected material, not a hoped-for breakthrough. Steel, oil, shock absorbers, and devices that several nations already manufactured in quantity. Design studies for an interstellar variant suggested cruise velocities somewhere between 3 and 10% of light speed. In a paper published in 1968, Dyson worked through a version that would reach Alpha Centauri in about 130 years. What is easy to miss about Orion is how large it was allowed to be and why that mattered. Nuclear pulse propulsion has an unusual property. It gets more efficient as the vehicle gets bigger because a larger plate catches more of each blast. Chemical rockets punish size. Orion rewarded it. The team studied a mid-sized version of around 4,000 tons that could have placed 1,600 tons of payload into orbit in a single launch, more than every mission of the Space Shuttle program combined, and Dyson sketched a version he called Super Orion at 8 million tons, a vehicle the size of a small city, because at that scale the arithmetic simply kept improving. For a brief period in the early 1960s, there were serious people writing serious memoranda about a crewed vehicle reaching Saturn and returning within a single year. There was also a cost that the team did not hide. Launching from the ground meant detonating hundreds of devices inside the atmosphere, and Dyson himself ran the calculation for the resulting fallout and its statistical consequences in human deaths per launch. He published the figure. He regarded it as unacceptable. He spent the rest of his life describing Orion as the greatest engineering opportunity of the 20th century and as a thing that should not have been built the way they wanted to build it, and he never seemed to find those two positions contradictory. The program was killed by a treaty. The Partial Test Ban Treaty of 1963 prohibited nuclear detonations in the atmosphere, underwater, and in space. Orion required nuclear detonations in space, several thousand of them per launch. Dyson himself supported the treaty, and said afterwards that he thought it was the right decision, and that it was also the end of the only starship he ever expected to see built. That is the first blueprint. Here is the second, and it is more detailed. Between 1973 and 1978, a volunteer team at the British Interplanetary Society, led by an engineer named Alan Bond and meeting largely in the evenings, produced a full design study for an unmanned starship. They called it Project Daedalus. The brief they set themselves was strict. Use only physics that was understood, use only engineering that could plausibly be developed within a few decades, and produce a vehicle that could reach another star within a single human working lifetime. They chose Barnard's star, about 6 light-years away, and gave themselves 50 years to get there. The vehicle they produced is the most thoroughly specified starship in history, and its numbers are worth hearing in full. Daedalus was a 2-stage vehicle with a launch mass of about 54,000 tons. 50,000 of those tons were fuel. The payload was 450 tons. Propulsion came from inertial confinement fusion, small pellets of deuterium and helium-3 injected into a magnetic reaction chamber and ignited by electron beams at a rate of 250 pellets every second. The first stage would burn for a little over 2 years, the second for nearly 2 more, and at the end of that burn the vehicle would be travelling at about 12% of the speed of light, roughly 36,000 kilometres per second, which is 2,000 times faster than Voyager 1. The helium-3 was a problem, because there is essentially none of it on Earth. The study's answer was to mine it from the atmosphere of Jupiter, using automated extraction plants suspended beneath hot air balloons, floating in the Jovian cloud tops, running for about 20 years to accumulate the required fuel load. The vehicle would then be assembled in orbit around Jupiter, because it was far too large to be built anywhere near a planet you might want to keep. The details go further, and it is the details that make Daedalus feel less like a fantasy and more like a document. The front of the vehicle carried a beryllium erosion shield weighing 32 tons, designed to absorb the impacts of interstellar dust across 6 light-years of flight. Ahead of that shield, the craft would deploy a cloud of fine particles to intercept larger grains at a safe standoff distance and blow them apart before they reached the hull. The payload bay held a 40-meter optical telescope and 18 autonomous subprobes, to be released years before arrival and fanned out across the target system, because the main vehicle would be moving far too quickly to loiter, and because no human crew could survive a 50-year flight in that machine, Daedalus carried 2 5-ton robots called Wardens, whose job was to walk the vehicle during the cruise and repair whatever broke. The study concluded in writing that no single nation could build it. It also concluded that nothing about it was impossible. Notice what those 18 sub-probes are for, because they are an admission. Daedalus arrives at Barnard's star travelling at 12% of light speed, and it has no way to slow down. There is no third stage, no braking burn, nothing in the mass budget for it. At that velocity, the vehicle crosses the entire inner region of a planetary system in a matter of hours. The probes exist because the mothership will be past the target before it can meaningfully observe it, so they are released years in advance to spread out and take their measurements in the seconds and minutes available, transmitting everything back to the main craft as it hurtles through. 50 years of flight, 4 years of engine burn, 50,000 tons of fuel, 20 years of mining Jupiter, and the science return is gathered during an encounter shorter than a working day by machines that are already leaving as they gather it. Nobody involved considered this a flaw. It was simply the mission. The alternative was not on the table, and in a few minutes I am going to show you exactly why. Daedalus was never meant to fly. It was meant to answer a question. Is a starship forbidden by physics, or merely expensive? And it answered it. Expensive. There were others. The Bussard interstellar ramjet, proposed by Robert Bussard in 1960, is the most beautiful idea in the entire field. A spacecraft that carries no fuel at all, spreading an enormous magnetic scoop ahead of itself to gather the thin interstellar hydrogen and feed it directly into a fusion reactor. No mass ratio, no Tsiolkovsky, constant acceleration forever on free hydrogen. It broke in 1985 when Robert Zubrin and Dana Andrews published an analysis showing that the magnetic scoop generates more drag than the fusion reaction can generate thrust above a few % of light speed. The ramjet does not accelerate you to relativistic velocity. It is, in fact, an outstanding brake, which is a sentence to file away because we will need it later. The Ensman starship, sketched in the 1960s, proposed a 12,000-ton sphere of frozen deuterium mounted at the nose, serving simultaneously as fuel and as radiation shielding, with the crew habitat trailing behind it. And in 2009, the Tau Zero Foundation and the British Interplanetary Society began Project Icarus, an explicit redesign of Daedalus for the modern era. Icarus differs from its predecessor in exactly one requirement, and that single requirement dominates the entire design. Daedalus was a flyby. Icarus has to stop. We will come back to what that costs. Step back and look at what this list actually shows, because it is not what people expect. The usual story about interstellar travel is that we do not know how. That story is false. We have known how since about 1958. There are folders, real ones, with page numbers and mass budgets and specified alloys, describing vehicles that would arrive at another star within a century of leaving. They were drawn by Nobel-caliber physicists and working aerospace engineers. They were reviewed, and they were published, and not 1 gram of any of them has ever been built. That is the pattern I want you to start watching for, because it repeats. It is not going to be the physics that fails in this story. Every single time we get to the end of a plan, the physics will have held up fine, and something else will have gone missing. Which brings us to the one that came closest, the only interstellar mission in history that ever got a stage, a press conference, and a check. Tear off a sheet of household cling film and hold it up to a lamp. Feel how little there is of it. Now imagine something less than a tenth that thick, made not of plastic but of silicon nitride, stretched across 4 meters and weighing about 1 gram, roughly the mass of a paperclip or of the folded corner of a banknote. Attached to it is a computer chip about 15 millimeters wide carrying cameras, a power source, a navigation system and a transmitter. That object, and nothing larger, is the most serious interstellar spacecraft anybody has ever attempted to build. And the reason it is that small is the arithmetic from a moment ago. If pushing 1 kilogram to a tenth of light speed costs 5 Hiroshimas, then the way to make a Starship affordable is not to build a better engine. It is to make the ship weigh almost nothing. There is a second move, and it is the clever one. Do not carry the engine at all. Leave it on Earth. The idea is older than it sounds. In the 1920s, Konstantin Tsiolkovsky, the same deaf schoolteacher from Kaluga, and a colleague named Friedrich Zander both proposed that sunlight itself could push a spacecraft, because light carries momentum even though it has no mass. The pressure is minuscule. Sunlight at the Earth's distance pushes on a perfect mirror with a force of about 9 micronewtons per square meter, which is roughly the weight of a grain of pollen. But it never stops. It costs nothing, and if the sail is light enough, a force that's small accumulates into something significant. Sunlight alone is far too weak for interstellar work. A laser is not. In 2009, a physicist from the University of California at Santa Barbara, named Philip Lubin, attended a conference at the Naval Postgraduate School in Monterey. The subject was directed energy, lasers, microwaves, particle beams, and the applications under discussion were mostly military, principally the destruction of incoming missiles. Lubin sat through it and started thinking about what else you could point that much energy at. Could you nudge an asteroid off a collision course? Could you push a spacecraft? He went home and began working through the numbers, and by his own account he was trying to prove himself wrong. I always want to figure out why it won't work, he said later. It kept working. After a meteor exploded over the Russian city of Chelyabinsk in 2013, and planetary defense became briefly fashionable, Lubin's directed energy research got funding and attention, and he began mentioning in talks that the same technology would enable interstellar flight. That mention travelled through a chain of introductions until, in January of 2016, he found himself sitting in a mansion in the Bay Area with a technology investor named Yuri Milner, his own roadmap on the table between them covered in yellow sticky notes. 3 months later, the plan was announced to the world as Breakthrough Starshot. Here is what it actually specifies. A conventional rocket lifts a mothership to orbit. The mothership carries a swarm of these gram-scale craft, each folded against its sail. When a craft has drifted to roughly 60,000 kilometers from Earth, about a sixth of the way to the Moon, a ground-based array of lasers begins to fire. The individual lasers are ordinary in power, but there are a great many of them, and their beams are combined into a single coherent beam carrying 100 gigawatts. 100 gigawatts is roughly the output of 100 large nuclear power stations all at once aimed at a paperclip. The beam fires for about 10 minutes. During those 10 minutes, the craft experiences an acceleration in the region of 40,000 times Earth gravity. At the end of them, the laser shuts off and the spacecraft is travelling at 20% of the speed of light, 60,000 kilometers every second. It coasts from there, unpowered, for about 21 years, and then it reaches Proxima Centauri, and it sends home what it saw, and that signal takes another 4 years and 3 months to arrive. Let me put you on it. You are the size of a postage stamp. Beneath you, 60,000 kilometers down, a patch of desert lights up in a way that has no precedent on this planet. There is no sound, no flame, no shudder, only a pressure that arrives instantly and evenly across 4 square meters of sail and does not let up. In the first second, you gain 400 kilometers per second. By the end of the first minute, you're moving faster than any object human beings have ever built, and you're still accelerating at 40,000 gravities, a force that would flatten a human being into a film thinner than paint. The Earth behind you shrinks with a speed that would be comical if anyone were watching in real time. At 2 minutes, you pass the Moon's orbit. At 10 minutes, the laser cuts out, and the last of its light chases after you and never quite catches up, and you're moving at 60,000 kilometers per second through a solar system that no longer has any hold on you at all. You will cross the orbit of Mars before the engineers at the array have finished writing down the telemetry. You will pass Neptune the following morning, and then you will fall silent and travel in a straight line for 21 years. That is not a fantasy. That is a funded engineering program with published specifications, and every one of those numbers comes from its own documentation. So what has to be true for it to work? The sail has to survive. It must reflect nearly all of the light that hits it, because whatever it absorbs turns into heat, and at 100 gigawatts, a fractional percent of absorption vaporizes the sail instantly. It must be almost perfectly thin and almost perfectly flat. The leading candidate material, identified by Harry Atwater's group at Caltech and published in 2022, is silicon nitride, which can be fabricated at sub-micron thickness while remaining reflective and structurally coherent. Small wafers of it can be assembled into larger sheets, at the millimeter scale, in a laboratory. Nobody has done it at the scale of meters. The laser has to be a single instrument. There is no such thing as a 100 gigawatt laser, and there is no prospect of one. What Starshot proposes is a phased array, many thousands of ordinary lasers whose beams are held in step with one another to within a fraction of a wavelength so that they add rather than interfere. Laboratory demonstrations have achieved this with tens of lasers. That was described correctly as a breakthrough. It is also roughly 3 orders of magnitude short. The atmosphere has to be cancelled. Any beam fired from the ground has to pass through the same turbulent air that makes stars twinkle, and a twinkling beam does not stay on a 4-meter target 60,000 kilometers away. The fix is a laser guide star. You fire a reference beam upward continuously, watch how the atmosphere distorts it, and correct the main array in real time. That correction has to be made millions of times per second across an aperture measured in kilometers. In a technical summary published in 2024, the project's own leadership identified this as potentially the single largest technical hurdle in the entire program. The economics have to change by 4 orders of magnitude. Laser power currently costs on the order of $100 per watt. For Starshot to be affordable, that figure has to fall to somewhere between 1 and 5 cents per watt. Everyone involved points to the history of semiconductors and says this is the kind of thing that happens. Everyone involved also acknowledges it has not happened yet. And then there is the problem nobody enjoys discussing, which is that a steerable 100 gigawatt laser array is not primarily a propulsion system. It is the most powerful directed energy weapon ever constructed, capable of reaching anything in near-Earth space and a great deal on the ground, and its funding, siting and operation would be a treaty negotiation before it was ever an engineering project. The technology that makes the stars reachable and the technology that makes orbit a shooting gallery are the same technology. Finally, the part that a physicist on the project called the elephant in the room. Suppose everything above works. Suppose your paperclip is at Proxima Centauri 21 years out, functioning perfectly, taking the first photographs of another solar system in human history. It now has to tell you. It has to send a detectable optical signal across 4.24 light-years, aimed accurately at a small moving planet, using a transmitter with a mass measured in fractions of a gram, and a power source you could not use to light a torch. The proposals are ingenious. Use the sail itself as the transmitting antenna, transmit in optical rather than radio wavelengths, aim at the sun as a beacon because it is a much bigger target than the Earth, and build an enormous array of small receivers here to catch whatever arrives. None of them has been demonstrated. Mason Peck, a Cornell engineer who was formerly NASA's chief technologist, and who worked on the project, made an observation about this that has stayed with me. Milner, he said, wanted photographs, high-resolution images from another star. Peck thought that was the wrong ambition. A single bit of information from another solar system, he argued, would be worth the entire mission. One yes or no. Is there oxygen in that atmosphere? Yes or no. It's only incrementally better, he said, to get a gigabit from Proxima Centauri. There is an answer to the failure rate, and it is the most robust idea in the whole architecture. Do not send one, send thousands. Build the array once and fire it repeatedly, launching a craft a day for years, so that no individual loss matters. Nature can destroy 90% of the swarm, and the mission still returns data. Which raises the question of what, exactly, is out there to destroy them. Because we have been talking about the gap between here and Proxima as 40 trillion kilometers of nothing. That was a simplification, and at 60,000 kilometers per second it becomes a dangerous one. Put a single grain of dust on your fingertip. Say it weighs a milligram, a speck you would need good light to see, the kind of thing that settles on a windowsill in an afternoon. It is inert. It is harmless. You could inhale it without noticing. Now hit it at 20% of the speed of light. That grain, at that velocity, carries about 1.8 billion joules of kinetic energy. That is roughly half a ton of TNT concentrated into an object smaller than a full stop, arriving with no warning and no possibility of deflection against a spacecraft that weighs 1 gram. This is the part of interstellar travel that almost never makes the diagrams, and it is the part that decides whether any of the rest of it matters. Interstellar space is, by any human standard, astonishingly empty. The local interstellar medium holds roughly 1 hydrogen atom per cubic centimetre. To appreciate that, consider that the air in the room you're sitting in contains something like 25 billion molecules in the same volume. The very best vacuum chambers ever built on Earth, the extreme high vacuum systems used in surface physics, pumped and baked for weeks, get down to perhaps 10,000 particles per cubic centimetre. Interstellar space beats our finest laboratories by a factor of 10,000. It is the emptiest thing there is, and it is still too crowded. The reason is that emptiness is not a property of the space. It is a property of the relationship between the space and the thing moving through it. At walking pace, 1 atom per cubic centimetre is indistinguishable from perfect vacuum. At 60,000 kilometers per second, your spacecraft sweeps up a column of that gas at a rate that turns it into something with a different name. A hydrogen nucleus hitting a stationary target at 20% of light speed arrives with an energy of about 19 million electron volts. That is not a gas. That is a particle beam, of the kind physicists build accelerators to produce, and your vehicle is flying nose first into it for 21 years without a magnetic field, without an atmosphere, and without a brake. In 2017, 4 researchers, Thiem Huang, Alex Lazarian, Blakesley Burkhart and Avi Loeb, published the analysis that put numbers on this, specifically for a Starshot-class craft. Their findings are precise, and they are unwelcome. Dust does the worst damage. A grain does not scratch the surface it hits. It deposits its entire energy in a volume of a few cubic microns in a few femtoseconds, and the material there does not melt or crack. It explosively evaporates, blowing a crater outward. Over a long enough flight, the accumulated craters become erosion. Their figure for a craft at 20% of light speed is that roughly half a millimetre of surface material is stripped away after the vehicle has swept through a hydrogen column density of about 3 times 10 to the 17th per square centimetre. Half a millimetre is not much for a hull. It is catastrophic for a sail that is less than a micron thick. Gas does a subtler damage. Individual hydrogen atoms mostly pass straight through a submicron sheet without depositing much energy. The sail is simply too thin to stop them. But the interstellar medium is not pure hydrogen. It carries heavier nuclei, and those leave damage tracks, narrow tunnels of disrupted crystal structure that accumulate until the material's optical and mechanical properties change. Their estimate is around 1/10 of a millimetre of degradation in quartz-like material after a swept column of about 2 times 10 to the 18th per square centimetre. The mitigation the authors recommend is worth sitting with because of what it says about the whole enterprise. Fold the sail, roll it up and retract it behind a small, dense, needle-shaped shield, presenting the smallest possible frontal area to the oncoming medium, and leave it that way for the entire cruise. The sail, the thing that makes the mission possible, the 4-metre sheet that is the entire reason this spacecraft can move at all, spends the journey rolled up and hiding behind a lump of metal. Daedalus had reached the same conclusion 40 years earlier by a different route. Its answer was 32 tons of beryllium across the nose, plus a deployed cloud of fine particles thrown ahead of the vehicle to intercept larger grains at a standoff distance and blow them apart before they reached the shield. A starship in every serious design we have spends its entire journey hiding behind something. The uncomfortable arithmetic underneath all of this is a probability rather than a certainty, and probabilities are exactly the wrong shape for a mission you only get to fly once. Large grains are rare. Most of the mass in the interstellar dust population sits in particles far smaller than a milligram, and a craft presenting a frontal area the size of a needle's tip might well cross 4 light-years without meeting anything big enough to end it. Might. Nobody can currently say with confidence what the population of grains above a microgram looks like along that specific corridor because we have never had an instrument out there measuring it, and the only way to find out is to send something and see whether it survives. This is where the swarm stops being a nice idea and becomes the entire strategy. You cannot armour a 1-gram spacecraft. There is no mass budget for armour. What you can do is accept that some fraction of your fleet will be quietly annihilated somewhere in the dark, at a moment nobody on Earth will ever be able to identify, and send enough of them that it does not matter. The mission survives by being expendable. Every individual craft is a coin flip, and the answer to a coin flip is not a better coin. It is 1,000 flips. Now for the piece of this that surprises people the most, because it is the opposite of what science fiction has trained us to expect. You might assume that a traveller at these speeds gets some relief from relativity, that time slows down aboard, that the trip is shorter for the crew than for the people at home. It does happen. It is real. And at 20% of light speed it is worth almost nothing. The Lorentz factor at that velocity is 1.02. Time aboard runs about 2% slower than time on Earth. A 21-year journey is experienced as roughly 20 years and 7 months. Distances ahead contract by the same 2%, so 4.24 light-years becomes 4.16. You would need a stopwatch to notice. Relativity's gifts only arrive at speeds far higher, and at those speeds the medium problem does not scale gently. It detonates. At 99% of light speed, the time saving becomes enormous, a factor of 7, but each interstellar hydrogen atom now arrives carrying billions of electron volts. The forward-facing hull is being irradiated by a beam comparable to what circulates inside a particle collider, and the cosmic microwave background itself, the 2.7 Kelvin afterglow of the Big Bang, the coldest, gentlest thing in the universe, is blue-shifted in the direction of travel until it becomes hard radiation. Going faster does not solve the medium. Going faster is how the medium kills you. There is one genuinely good piece of news in all of this, and it deserves saying because there is not much of it in this subject. Our particular route is unusually clear. The Sun sits inside a wisp called the local interstellar cloud, about 30 light-years across, and that cloud sits inside a much larger structure called the local bubble, a cavity roughly 1,000 light-years wide, blown clear of gas and dust by a series of supernovae several million years ago. We are, at this moment in galactic history, living inside a hole. The corridor between here and Proxima Centauri is about as thin as interstellar space gets. If our species is ever going to attempt this, we happen to be attempting it from a good address. Let me stop and restack everything, because we are halfway, and the pieces have been arriving faster than they can be held. We started with a real destination 4.24 light-years away, with a rocky planet in the habitable zone of an invisible star. We found that the fastest machines we have ever built would take 75,000 years to get there, and that they were never designed for it anyway. We found that the reason nothing better exists is not a missing invention but a logarithm, that chemical propulsion is arithmetically disqualified, and that the raw energy required to push even a small ship to 1/10 of light speed is comparable to a year of planetary civilization. We found that human beings have already designed vehicles that would beat that problem, twice in detail, using fusion and using nuclear pulse, and that none of them was ever built. We found a third design that dodges the fuel problem entirely by leaving the engine on the ground and shrinking the ship to the mass of a paperclip. And now we have found that the emptiness the whole plan relies on is not empty enough, and that the sail has to hide behind a shield for 21 years to survive the crossing. Every one of those obstacles has an answer. That is the thing to notice. Not one of them is a wall, each is a bill, and each bill is payable by a civilization that decided this mattered. Which is why the next one is different. Because the next problem does not have an answer. It is not a matter of scale or money or patience, and almost nobody who talks enthusiastically about interstellar travel in public will mention it to you unless you ask. The ship gets there. Nobody ever explains how it stops. At 20% of the speed of light, you cross the distance between the Earth and the Moon in 6.5 seconds. You cross the distance between the Earth and the Sun in about 42 minutes. The entire orbit of Proxima Centauri b, the whole habitable zone of the nearest star, the target of the mission, the reason for the journey, is roughly 14.5 million kilometers across, and you pass through all of it in 4 minutes. 4 minutes. 21 years of flight, 100 gigawatts, a laser array the size of a city, and the encounter with the destination lasts about as long as it takes to boil a kettle. And that is if everything goes perfectly, because Breakthrough Starshot has no brakes. It cannot have brakes. This is not an oversight in the design. It is the design. The entire architecture works because the propulsion system stays on Earth. That is the trick that gets around Tsiolkovsky's logarithm. You never carry your fuel, so the mass ratio never bites. But the moment you ask the craft to slow down at the far end, you're asking it to carry an engine after all, and the whole beautiful structure collapses back into the equation it was built to escape. There is no laser array at Proxima Centauri, there is nobody there to switch one on, so the spacecraft arrives, and it does not stop, and I want you to be there for it. You have been dark for 21 years. Nothing has happened. The star ahead has been a point of light growing imperceptibly brighter for 2 decades, and now, in the final weeks, it begins to change quickly. Then, in the final hours, it becomes something with a size. Your instruments, cameras, a spectrometer, a magnetometer, none of them larger than a grain of rice, come out of their long sleep and begin recording everything, in every direction, as fast as their tiny power supply allows. The star swells. A planet resolves from a point into a disk, and for a handful of seconds it is a world, a hemisphere in shadow, a hemisphere in red light, a limb, an edge, a curve that no human eye has ever seen. And then it is behind you. You do not slow. There is nothing aboard that could slow you, and there never was. The star that took 21 years to reach recedes as fast as it approached. The planet shrinks back to a point and then to nothing, and your transmitter begins pushing the data you gathered back toward a world 4 light years behind you, where it will arrive in another 4 years and 3 months, by which time you will be a further 800 billion kilometers out. You keep going. You will keep going forever, at 60,000 kilometers per second, out of the Alpha Centauri system, out through the local neighborhood, out into the galaxy, and there is no next destination and no plan for one. You're the first object from Earth to reach another star, and you did it by passing it. There is a companion problem hiding inside that flyby, and it is worth a moment because it explains why the 4 minutes might easily be 0. You have to hit the thing, not the star system, a specific planet within a few 100,000 kilometers after 21 years of unpowered flight, having been aimed by a laser array on a rotating planet at a target that is itself moving. Proxima Centauri is not sitting still. It has a proper motion across our sky of nearly 4 seconds of arc per year, which is among the largest of any star, and over 21 years that carries it a noticeable distance. You're not aiming at where it is. You're aiming at where it will be in 21 years, using a position measurement taken now, with no course corrections available beyond whatever tiny attitude thrusters a gram-scale chip can carry, and no navigation updates because the round-trip signal delay by the time you would need one is longer than the remaining flight. It is the ballistics problem of hitting a coin in another city with a rifle, if the coin were also moving and you had to fire before you were told where it was going. This is not unsolvable. Astrometry from Gaia has pinned nearby stellar motions to remarkable precision, and a swarm of thousands can be fanned across the uncertainty. But it is one more reason the mission is designed as a fleet rather than a ship, and one more reason that the phrase reaching Proxima Centauri contains more assumptions than it looks like it does. Here is why stopping is so much worse than going, stated as plainly as I can. Kinetic energy does not care about direction. If it took a certain amount of energy to accelerate you to a speed, it takes the same amount to remove that speed. There is no cheaper way to lose it. You can radiate it, you can push against something, but you cannot simply decide to stop. And if you intend to carry the means of braking with you, that braking fuel is itself mass that has to be accelerated at the start, which means more fuel to accelerate it, which means more fuel to accelerate that. The mass ratio does not double, it squares. We already learned this one scale rung down, and we learned it the expensive way. Mercury is the closest planet to Earth for most of the time, and it took Messenger 6.5 years and 6 separate gravity assists to enter orbit around it. Not because Mercury is far, but because falling toward the Sun makes you faster, and all of that extra speed has to be shed before you can be captured. New Horizons reached Pluto in 9.5 years and could not stop, because carrying enough propellant to enter Pluto orbit would have required a launch vehicle roughly 4 times the mass of the one that flew. We got 9 days of close observation of Pluto and its moons, and then it was gone, and it will not be back. In the solar system, arriving somewhere costs several times more than reaching it. Between stars, that ratio is far worse. There is one genuinely elegant escape route, and it deserves proper attention because it is the best idea anyone has had about this. In 2017, René Heller and Michael Hipka published a paper proposing that a light sail could be stopped using the destination itself. Alpha Centauri A and B are bright, sun-like stars, and bright stars push. A sufficiently light sail arriving at the right angle could be slowed by the radiation pressure of the stars it is arriving at, and steered by their gravity, a maneuver they named the photogravitational assist. It is the gravity assist trick that got Voyager to Neptune, run in reverse, with light doing the braking. It works, and the price is written into the arithmetic. To be captured rather than flung past, the sail has to arrive slowly, because starlight is not that strong. Heller and Hipker calculate a maximum injection speed at Alpha Centauri A of about 13,800 km per second, 4.6% of light speed, less than a quarter of the Starshot cruise velocity. At that speed, the crossing from Earth to Alpha Centauri A and B takes about 95 years. The craft is then handed on by a second maneuver to Proxima Centauri, which takes a further 46 years, because Proxima is faint and its light is a much weaker break, and it sits a good fraction of a light year off to one side. 95 years plus 46, about 141 years to arrive somewhere, against roughly 21 years to fly past. There is a further condition. The sail that carries a payload of 10 grams under this scheme needs an area of about 100,000 square meters, a square roughly 316 meters on a side, at an aerial density comparable to graphene, unfurled and held flat and undamaged across 4 light years and a century and a half of flight, after we established a few minutes ago that a 4-meter sail has to spend the journey rolled up behind a shield to survive at all. The other braking proposals have the same shape. Magnetic sails, proposed by Robert Zubrin and Dana Andrews in 1988, would deploy a superconducting loop kilometers across and brake against the interstellar medium, using the thin plasma as a parachute. It works well at high speed and progressively worse as you slow, because the drag depends on how fast you're ploughing through the plasma, so the deceleration has an enormous asymptotic tail, and the last few percent of the braking takes as long as everything before it. The Bassard ramjet, which fails as an engine, works beautifully as a brake for exactly the same reason its drag defeated it in the first place. And this is precisely the difference between the two great fusion starships. Project Daedalus, in 1978, was a flyby, and it weighed 54,000 tons. Project Icarus, its modern successor, has one additional requirement in its brief. It must enter orbit, and that single line item dominates the entire design, because every kilogram of braking capacity must be dragged through the acceleration phase first. So here is where we stand, and it is a strange place to be standing. Every fast method we have works. The physics holds. A gram-scale craft on a laser beam will get to Proxima Centauri in about 21 years, and if we started building the array this decade, there are people alive today who would see the pictures. That is a real sentence about a real possibility, and it is remarkable. And in every one of those methods, the spacecraft reaches Proxima Centauri at a fifth of the speed of light and keeps going. It does not orbit. It does not land. It does not stay. It takes 4 minutes of data on its way through and spends the rest of eternity leaving. There is a word we have been using loosely, and it is time to be precise about it. Reaching a place and arriving at a place are not the same event. Everything we can currently build reaches Proxima Centauri. Nothing we can currently build arrives there, unless, of course, you stop trying to make the vehicle stop, and instead make the journey itself the place you live. On the 26th of September, 1991, in the desert north of Tucson, Arizona, 8 people in dark jumpsuits walked through a steel airlock and stood together while it was closed and sealed behind them. Above and around them stretched 3 acres of white steel framing and glass, a structure that looked like a cross between a cathedral and a greenhouse, containing a small rainforest, a savanna, a mangrove wetland, a fog desert, a farm, and an ocean, with a coral reef and a wave machine. Inside were roughly 3,800 species of plants and animals. The building was called Biosphere 2, on the reasoning that Biosphere 1 was the Earth. They were going to stay for 2 years. They were going to grow all of their own food, breathe air that the plants inside regenerated, and drink water the system recycled, taking nothing at all from outside except sunlight and electricity. It remains the most ambitious closed ecology experiment anyone has ever run, and it is the closest thing we have to a test of the idea that a group of human beings can be sealed inside a machine and survive. Within a few months, the oxygen started disappearing. The atmosphere inside had begun at the normal 20.9% oxygen. Over the following 16 months it fell, steadily and without explanation, to about 14.5%. That is the oxygen level you would find at an altitude of around 4,000 meters, high in the Andes, well above the height at which unacclimatized people begin to suffer. The crew developed sleep apnea and chronic fatigue. They struggled to complete physical tasks they had managed easily at the start. One crew member reported being unable to finish a sentence without pausing for breath, and another was later found to have lost the ability to add a column of numbers reliably, and nobody could work out where the oxygen was going. Carbon dioxide was not building up to match, which is what you would expect if respiration was simply outpacing photosynthesis. Oxygen was leaving the system, and its carbon partner was not appearing anywhere. It took a chemist from outside, Jeff Severinghaus, running isotope analysis, to find the answer, and the answer was so mundane that it is almost funny. The concrete was eating it. The soils inside Biosphere 2 had been enriched with organic matter to support intensive agriculture, and the microbes in that soil were respiring far faster than anyone had modelled, consuming oxygen and producing carbon dioxide exactly as they should. But the structure contained an enormous quantity of exposed uncured concrete, and curing concrete absorbs carbon dioxide, binding it permanently into calcium carbonate. So the carbon was being locked into the walls, which meant the plants never got it back, which meant they could not return the oxygen. The loop was not closed, it was leaking into the building itself. In January of 1993, with the crew's health deteriorating, oxygen was pumped in from outside. The experiment's central claim, full closure, was over. The rest of the ledger is not much better. 19 of the 25 vertebrate species introduced went extinct inside the 2 years. Almost all of the pollinating insects died, which meant many of the plants could not reproduce. Ants and cockroaches, which nobody had intended to include, thrived and took over. Crop yields fell short of what the crew needed, and every member lost significant body weight in the first year. And somewhere in the middle of it, under the pressure of hunger and hypoxia and confinement, the 8 people split into 2 factions that stopped speaking to one another socially and communicated only about work. Several of them were still not on speaking terms years later. Now hold that up against what a generation ship actually requires. Biosphere 2 sat on the ground. It had unlimited electrical power from the grid. It had a real sun overhead. It had an entire planet's worth of engineers, chemists and doctors on call outside the glass, watching every gauge. It had spare parts available same day. It ran for 24 months, and it had a door. A starship has none of those things. It must close carbon, nitrogen, water, oxygen and phosphorus completely, with no resupply, no external expertise, no sunlight, and no exit. Not for 2 years, but for somewhere between 2 centuries and 6,000, depending on how fast you can make it go. And you already know how fast you can make it go, because we did that arithmetic. A 1,000-ton vessel at 1/10 of light speed costs most of a year of global energy production, and a generation ship is not 1,000 tons. Serious designs run from tens of thousands of tons into the millions. The mass that makes it survivable is precisely the mass that makes it slow. A ship big enough to be a world cannot be fast, and a ship fast enough to arrive within a lifetime cannot be a world. The reason full closure is not optional becomes obvious the moment you weigh a person. A human being consumes roughly 0.8 kilograms of oxygen, 3.5 kilograms of water, and about half a kilogram of dried food every day, and produces a corresponding mass of carbon dioxide, moisture, and waste. Call it 5 kilograms a day of throughput, which is around 1.8 tons per person per year. A crew of 100 people, over a 300-year voyage, therefore moves about 54,000 tons of material through their own bodies, and that is a modest crew on a fast ship. Carrying that as cargo is not an option at any speed. Every gram of it has to go round again, and again, and again, thousands of times, through soil and water and air for centuries, without the loop losing more than a rounding error at each pass. Biosphere 2 lost its loop to a wall. There is no reason to believe we would find the next leak before it found us. There is something almost restful about picturing the place where all of this would have to happen, and it is worth a moment in the middle of the arithmetic. Imagine standing inside a cylinder 8 kilometers long and 1.5 kilometers across, turning slowly enough that you never feel it turn. The ground curves upward on both sides and continues over your head, so that when you look straight up you see farmland, a river, the roofs of a settlement, all of it hanging there, right way up from someone else's point of view. Long strips of window run the length of the hull, and behind them, instead of sky, a diffuse light panel brightens and dims on a schedule someone chose. There is weather of a kind, condensation, drifting cloud, a light rain in the afternoons because the humidity engineers wanted one. There are birds, and beyond the glass, unmoving, unchanging, the same stars in the same places for the whole of your life. So the vessel must be large, and it must spin, because human bodies fall apart in weightlessness over decades. Bone loss, muscle atrophy, fluid shifts, vision damage, and no one has ever tested what happens to a human being, let alone a pregnancy, over a lifetime in zero gravity. Spinning means a cylinder, kilometers long, rotating perhaps once a minute, and a rotating structure of that scale has its own problems. Any mass that moves inside it changes its balance, and a wobble that develops in a spinning object several kilometers long is not a thing you correct with an afternoon of maintenance. It must be shielded, because outside the Earth's magnetic field, there is a constant sleet of galactic cosmic rays that will accumulate in tissue over decades. The standard answer is meters of water or packed rock around the inhabited volume, which is effective and which adds tens of thousands of tons to the mass that has to be accelerated. And then there is the problem that quietly worries engineers more than any of the above, which is that things break. Take a component with a 99.99% chance of surviving each year, extraordinarily reliable by any standard, a rate you would be delighted with in an aircraft. Over 1,000 years, that component has roughly a 90% chance of failing at least once. Now put several million such components into one vehicle. Over the mission, every single one of them will fail, most of them many times. There is no resupply, there is no factory, there is no shipping, which means the vessel cannot merely carry supplies. It has to carry the capacity to make things, to mine raw material from stores, to smelt it, to machine it, to fabricate electronics, to manufacture pharmaceuticals, to grow replacement seed stock. A generation ship is not a vehicle with a crew. It is a self-sufficient industrial civilization that happens to be moving, and it has to remain self-sufficient and industrially competent for longer than the interval separating us from the Roman Empire. For perspective on how far that is from anything we have ever done, the oldest human artifact still in orbit is Vanguard 1, launched in 1958. It is a sphere the size of a grapefruit. It has been silent since 1964. No machine built by human beings has ever operated continuously for more than a few decades, and the ones that come closest are the two Voyagers, which are 200 kilograms of 1970s electronics with no moving parts and nothing to keep alive. This is the design brief that gives the generation ship its defining phrase, and it is a phrase worth remembering because it changes meaning later. On a voyage like this, the ship is not transport. The ship is the world. Everything that exists for the duration is inside the hull. Every ecosystem, every industry, every institution, every relationship, every possibility. That is an engineering statement. It is a way of saying that the vessel must be complete. It is also, if you turn it very slightly, a description of a life sentence, and the people it describes are not the ones who signed up. Picture 98 people in a room. It is a large seminar hall, or a small village hall, or the guest list of a modest wedding. You could learn all of their names in a fortnight. You could learn all of their faces in an afternoon. That is the smallest number of human beings that can be sent to another star with any realistic chance of anyone surviving the trip. It is not a guess. It came out of a computer. In 2017, an astrophysicist named Frédéric Marin at the Astronomical Observatory of Strasbourg, working with a particle physicist named Camille Bellouffi, published a piece of software in the Journal of the British Interplanetary Society. They called it Heritage, and it does something nobody had done properly before. It simulates a multi-generational crew year by year for the entire duration of an interstellar voyage. It tracks every individual. It models births and deaths, fertility windows, pairing, accidents, disease, and, crucially, the degree of genetic relatedness between any two people who might have children together. Then it runs the whole thing thousands of times over as a Monte Carlo simulation and reports how often the population is still viable at the end. In 2018, they pointed it at the obvious target. The reference mission was a voyage to Proxima Centauri b lasting 6,300 years. The answer, under conservative assumptions, was 98 settlers. Below that, the arithmetic of relatedness begins to close in, with a starting crew of 32, which is roughly the size of a nuclear submarine's watch section, and a number that a great deal of science fiction would consider generous. The simulated success rate is 0%. Not low, 0. Every run collapses because in a closed population that small, within a handful of generations everyone is everyone's cousin. and the accumulated recessive burden does the rest. I want to be careful about what that number 98 actually is, because it is easy to hear it as reassuring. It is not a recommendation. It is a flaw computed under conditions of remarkable good fortune. No epidemic, no systems failure, no fire, no reactor problem, no schism, no murder, no loss of the will to continue. It is the answer to the question, what is the smallest crew that genetics alone does not kill, and genetics alone is the least of what is out there. Other people have run the same question with different amounts of caution and got very different answers. The anthropologist John Moore, looking at a 200-year voyage in 2002, suggested around 160. Cameron Smith, another anthropologist, published a much more conservative analysis in 2014, arguing for a minimum near 10,000 and a comfortable figure in the region of 40,000. That is disagreement spanning more than 2 orders of magnitude, and it is worth understanding why, because the disagreement is not really about biology. It is about how much bad luck a plan should be able to absorb. Marin and Beluffi are answering a mathematical question. Smith is answering a question about what happens when a plague sweeps through a closed population of 200 in year 400, and nobody thought to build in redundancy for that. Conservation biology has a rule of thumb for exactly this problem, developed for endangered species. 50 individuals to avoid immediate inbreeding depression, 500 to retain enough variation to keep adapting over the long term. Later work has argued that even 500 is too low. Whichever figure you take, the underlying principle is unforgiving and it has a name. It is called the founder effect, and it means that whatever genetic variation walks up the ramp on launch day is all the variation that will ever exist. Every gene not aboard is gone, not scarce, gone permanently, for every human being who will ever live in that lineage and for every human being on the world at the far end. Which brings us to the people who are actually going to make this journey, and they are not the ones in the promotional video. You are born in year 300. The ship left before your great-great-grandparents were born, and it will not arrive until 50 generations after you're dead. You have never seen a horizon. The ground curves upward in every direction and closes over your head. You have never seen weather that nobody scheduled. You have never seen an animal that was not on the manifest, or eaten a food that was not grown in a facility 3 corridors from where you sleep. Your species, so far as your senses have ever reported, consists of about 200 people, all of whom you know, most of whom you are related to. Earth is a place in the archive. You have seen the pictures, in the way that you have seen pictures of the Bronze Age, and they are equally relevant to your afternoon. Proxima Centauri is a slightly brighter point in a starfield that has not visibly changed in your entire life, and it will not visibly change in your children's. You will be born in transit, you will live entirely in transit, and you will die in transit, and every hour of your life will be spent maintaining a machine whose purpose is to deliver strangers to a destination you do not get to see. Here is the part that I find genuinely difficult, and I do not think there is a comfortable way through it. The first crew volunteered. Whatever they gave up, they chose to give up with full information, presumably after a great deal of thought. Nobody after them chooses anything. The child born in year 300 did not consent to a sealed world, a fixed population, a mandatory occupation, and a life without options, and there is no mechanism by which they could have. And their alternatives, once they are old enough to resent it, are essentially 2: continue or end the mission. Ending it means that everything every previous generation paid for was wasted, and that everyone born after them inherits a drifting hulk instead of a purpose. So they continue, not because they agreed, but because refusing costs more than complying. That is a moral structure with a name in every other context, and it is not a flattering one. It is also, as far as anyone can see, unavoidable. You cannot get a species across 4 light years without somebody being born inside the attempt. We have small hints about how humans handle even the mild version of this. The Mars 500 experiment, run between 2010 and 2011, sealed 6 volunteers into a simulated spacecraft in Moscow for 520 days. There was no physical danger whatsoever. The door was not locked. The crew could have walked out at any moment, and everyone knew it. By the end, one crew member's sleep cycle had drifted so far that he was essentially living on a different schedule from everyone else. 2 had developed significant sleep disorders, and the crew's total communication with mission control had dropped substantially as they withdrew into themselves. Antarctic research stations report something similar and consistent enough to have a name in the literature: winter over syndrome, a cluster of cognitive slowing, irritability, insomnia and low mood that sets in after months of confinement and darkness. Those people are volunteers on a paid contract for a fixed term with a plane coming in the spring. None of them is an analogue for a life sentence handed down before birth. And then there is the slow problem, the one that no simulation captures. Language drifts. 6,000 years is more than twice the distance between us and Homer, and roughly the interval between us and the invention of writing. Institutions drift. Purposes drift. A mission plan is a document, and documents become texts, and texts become scripture, and scripture becomes something people argue about and eventually reinterpret. Somewhere in the middle of a 6,000-year voyage, the founding decision is no longer a decision anyone can remember being made. It is simply the way things are, defended by whoever benefits from things staying that way. Remember what the engineers meant when they said the ship is the world. They meant it as a specification. The vessel has to be complete because there is no resupply. For the people born inside it, it is not a specification. It is a fact about the universe. The ship is the world. There is no other one, not in any sense their senses can verify, and the destination is a rumour told by people who died 400 years ago. There are two proposed escapes from the consent problem, and both are worth stating because both fail in instructive ways. The first is suspended animation. If you could suppress human metabolism deeply enough, the crew that leaves would be the crew that arrives, the middle generations would never exist, and the whole moral structure evaporates. The trouble is that we are nowhere near it. Therapeutic hypothermia in intensive care buys hours, occasionally days. Genuine hibernation in mammals is a metabolic state we do not know how to induce in a primate. And even in hibernating species, the animal wakes periodically because the body cannot be left indefinitely at low temperature without damage. Worse, metabolic suppression does nothing about radiation. Cosmic rays keep arriving, and a body that is not repairing itself is a body accumulating damage with the repair mechanism switched off. Sleeping through the journey may be strictly worse than living through it. The second is to send no adults at all. Embryo space colonization proposes carrying frozen embryos gestated by machines on final approach, with artificial systems raising the first generation. It removes the sealed centuries and replaces them with a question nobody can answer: whether a human being raised entirely by machines, with no living culture to inherit, arrives as a person capable of founding a civilization or as something else. So that is the human route to arrival. It works, and the cost is that the arrival belongs to people who are not us, on a vessel that has become its own civilization, carrying a purpose it inherited rather than chose. Which raises a very reasonable question, and it is the question that has quietly stopped every interstellar program in history. If we know all of this, if we can see the cost, and see how much better the technology is getting every decade, why on earth would anyone launch now? Stand on a dock in Liverpool in the middle of the 19th century with a ticket in your hand. The ship in front of you is a sailing packet, and it will take you to New York in about 6 weeks if the weather is kind and rather longer if it is not. You have heard that the steamship lines are improving quickly, that within a few years the crossing will be down to 10 days, reliably, on a schedule. You could go now and spend 6 weeks at sea, or you could wait 5 years and arrive sooner in total, having spent most of the interval at home. That is a real decision, and people made it. Now stretch it across 4 light years, and it stops being a travel choice and becomes something closer to a paradox. In 2006, an engineer named Andrew Kennedy published a paper in the Journal of the British Interplanetary Society with a title that sounds dry and an argument that has haunted the field ever since: interstellar travel, the weight calculation, and the incentive trap of progress. The argument is arithmetic, not psychology, and it goes like this. Suppose the maximum speed our vehicles can achieve improves at some steady annual rate, not dramatically, just the ordinary compounding improvement that technology has shown for centuries. Now suppose you launch a starship today, at today's best speed, on a voyage of several hundred years. Somewhere out there in the dark, decades or centuries after you left, a faster ship departs Earth, built with technology that did not exist when you launched, and it passes you. It arrives first. The colony is founded by people who left long after you did, and your ship shows up years later to find the job done, the land taken, and your entire enterprise reduced to a historical curiosity. If that is the likely outcome, then leaving now is irrational, not cowardly, irrational. You would arrive later, at greater cost than if you had simply stayed home and let the technology mature. So you wait. And the sensible thing about waiting is that it is sensible. But the person standing in your place 10 years from now runs exactly the same calculation, with exactly the same structure, and reaches exactly the same conclusion. And so does the person a century after that. Put actual numbers on it, and the sting is easy to feel. Say a ship departs for Proxima Centauri at 1% of light speed. The crossing takes 424 years, so it arrives in the year 2450. A century later, on a planet where propulsion has quietly kept improving, a second ship departs at 3% of light speed. Its crossing takes 141 years, so it arrives in the year 2267, 183 years before the first ship gets there. The people on the first ship are 12 generations in, maintaining their systems, teaching their children the mission, when the second ship passes them in the dark. They would not even see it go by. And when they finally arrive, 3 lifetimes late, they arrive as immigrants to a settlement founded by people whose grandparents had not been born when they left. That scenario has a name in the literature, and the name tells you how seriously it is taken. It is called being overtaken, and every serious proposal for a slow-crewed mission has to argue its way past it. The trap has a second form that operates on institutions rather than travellers, and this one is not hypothetical at all. Nobody wants to fund the ship that gets overtaken. A national space agency asked to commit to a 400-year program is being asked to spend present money on a return that will accrue, if it accrues at all, to a political entity that may not exist and to people who will not remember whose budget line it came from. The rational bureaucratic move is identical to the rational traveller's move. Defer, study, keep the option open, and let the next administration decide. And so the money goes to a study, and the study concludes that the technology needs another decade, and the decade passes. Kennedy worked the numbers for Barnard's star, about 6 light-years away, assuming a modest 1.4% annual growth in achievable velocity. He found something genuinely surprising. There is a minimum. If you add the waiting time to the travel time, and look for the point where the total is smallest, the answer is not now, and it is not never. It comes out at roughly 712 years from the date of the paper. Launch earlier than that, and you will be overtaken. Launch later, and you have simply wasted the interval. The optimal departure date for the nearest reasonable destination is somewhere in the 27th century. 11 years later, in 2017, René Heller, the same physicist behind the photogravitational braking scheme, published a relativistic generalization of Kennedy's argument in monthly notices of the Royal Astronomical Society, applying it directly to breakthrough starshot. He looked at 211 years of historical speed records for human vehicles and derived a growth rate closer to 4.72% per year, which shortens the optimal weight considerably. It does not remove the structure. The trap is not sensitive to the exact number. It is a consequence of the shape of the situation. Now, there is a hole in this argument, and it is a large one, and I think it is the most interesting thing in this entire part. The trap eats itself. All of that projected growth in velocity, the growth that makes waiting rational, comes from somewhere. It comes from people building things, testing things, failing at things, and iterating. It comes from precisely the programs that the weight calculation tells everyone not to fund. If every generation looks at the curve and concludes that the smart move is to defer, then nobody builds anything. The curve flattens, and the assumption that justified the deferral quietly stops being true. The incentive trap is a prediction that destroys its own premises, and here is the part that should make you sit up, because we can check whether it has already happened. The fastest human beings have ever travelled remains about 39,900 kilometers per hour, set by the crew of Apollo 10 in May of 1969. That record is 57 years old. The furthest any human has ever been from Earth was set in April of 1970, and we have not been back. The fastest uncrewed object is the Parker Solar Probe, and as we established, that figure is a falling speed rather than a cruising one. It is the number you get from dropping something toward the sun, not from building a better engine. Strip that out and the honest cruise velocity record for a spacecraft leaving the solar system is still held by a vehicle launched in 1977. Kennedy's curve assumes compounding growth in velocity. For the last half-century, in the specific quantity that matters, the curve has been flat. If that continues, the incentive trap dissolves, and what replaces it is considerably worse, because if speed is not improving, then waiting buys nothing at all, and every year of deferral is simply a year subtracted from the total. The rational argument for waiting turns out to have been resting on an assumption that stopped being true around the time the last person walked on the moon, and nobody updated it, because nobody was launching anything anyway. I want to be fair to the other side because there is a genuine counter-argument, and it is a good one. Growth did not stop. It moved sideways. The last 50 years produced almost no improvement in how fast we can push a large mass, and an improvement of many orders of magnitude in how small a functioning spacecraft can be. Breakthrough Starshot does not exist because engines got better. It exists because a camera, a computer, a power supply and a transmitter can now weigh a gram, and because lasers and photonics improved beyond anything imaginable in 1977. The curve that mattered turned out to be a different curve. Someone running the weight calculation in 1970, using velocity as their metric, would have concluded that interstellar travel was as far away as ever, and they would have been staring straight past the technology that actually opened the door, which suggests that the weight calculation, for all its elegance, may be answering the wrong question. It asks when to leave, assuming we know what leaving will look like. The historical record suggests we usually do not. There is a final consideration that the mathematics does not include, and it is the one that gives the whole thing its edge. The weight calculation assumes the waiting civilization is still there. It treats the future as a reliable supplier of better ships. Every generation that defers is making a bet not just about technology, but about continuity, about there still being observatories and funding bodies and a species with the attention span to care about a star it cannot see. That is not a bet with a track record. That is a bet on something nobody has ever tested. And all of this, every equation, every design, every simulated crew, every deferred launch, has been about how to get there. We have not yet asked the simplest question in the entire subject. What is actually waiting at the other end? On the 18th of March, 2016, a bank of small telescopes in northern Chile called Everescope was doing what it does every clear night, photographing the entire visible sky at once, every 2 minutes, looking for anything that changes. At one point in that night's sequence, Proxima Centauri got brighter, not slightly. Over about 2 minutes, the faintest, dimmest, most modest star in our neighbourhood brightened by a factor of 68 in visible light, and for a short interval it crossed the threshold of naked-eye visibility. If you had been standing outside in the southern hemisphere at that exact moment, looking at the exact right patch of apparently empty sky, you would have seen the nearest star to the Sun with your own eyes, for the first time in the history of our species, and then watched it fade back into invisibility. That event was published by Ward Howard and colleagues in 2018, and their analysis suggested that flares of that class happen at Proxima about 5 times a year. 3 years later, something more extreme was caught, and it was caught properly. In 2019, a campaign led by Meredith McGregor pointed 9 instruments at Proxima Centauri simultaneously, on the ground and in space, from radio through millimeter and optical to the ultraviolet, and watched for 40 hours spread across several months. In May, 5 of those instruments recorded the same thing at the same moment, a flare lasting about 7 seconds, during which the star brightened by more than a factor of 1,000 in millimeter wavelengths as seen by ALMA, and by more than a factor of 14,000 in the ultraviolet as seen by Hubble. It remains the most thoroughly observed stellar flare other than the Sun's, and McGregor's summary of what it means for anything orbiting there was not hedged. Proxima Centauri's planets, she said, are getting hit by something like this not once in a century, but at least once a day, if not several times a day. Now put the planet back into that picture. Proxima Centauri b orbits at 0.0485 astronomical units. That is under 5% of the distance from the Earth to the Sun, closer to its star than Mercury is to ours by a factor of about 8. It completes an orbit every 11.186 days. At that distance, tidal forces almost certainly have it locked, one face permanently toward the star and one permanently away, with a terminator line of eternal twilight between them. The only escape from that is if its orbit is more eccentric than about 6 to 10%, in which case it may instead be caught in a Mercury-like resonance, spinning 3 times for every 2 orbits. Being in the habitable zone, at that distance means one thing and one thing only. The equilibrium temperature is in the right band for liquid water, That is a statement about how much heat arrives. It is not a statement about whether anything can live there, because what also arrives several times a day is hard ultraviolet and X-ray radiation from a star that is quite happy to increase its own brightness 14,000-fold in 7 seconds. That kind of radiation dissociates water molecules and destroys ozone, and flares of that magnitude are typically accompanied by coronal mass ejections, enormous slugs of magnetized plasma flung outward, which over geological time strip the atmosphere off any planet without a strong magnetic field to deflect them. Proxima b sits 20 times closer to its star than we do to ours, so it receives those ejections at correspondingly brutal intensity. Stand on the day side for a moment, because it is worth seeing even if nothing can see it. The star hangs in the sky and does not move. It is not a small distant disk like our Sun. From that orbit it would appear roughly 3 times wider, filling a noticeable patch of sky, and it is red. A dull, sullen red, because most of its output is in the infrared, and what reaches your eyes is the thin end of it. There is no sunrise because the star never rises. There is no sunset because it never sets. Your shadow points in the same direction for every hour of every year, and it does so forever. Walk far enough toward the horizon, and you reach the terminator, a band of permanent copper twilight ringing the planet, and beyond it a hemisphere that has been in darkness since the world formed. And then, on no schedule you could predict, the fixed red disk above you flares, brightening by a factor of dozens in the time it takes to draw breath, and the sky floods with ultraviolet light that would burn unshielded skin in minutes, and then it fades, and everything is exactly as it was, and it will happen again tomorrow. To be fair to the planet, that is not the only possible picture. Some climate models suggest that a sufficiently thick atmosphere could carry heat around to the night side and keep the whole world habitable rather than half scorched and half frozen, and a strong magnetic field would help considerably against the ejections. Nobody knows whether Proxima b has either. Those are exactly the questions a probe would answer, and exactly the questions we cannot currently answer from here. No atmosphere has been detected at Proxima b. It may have one. It may have had one for a while. As things stand, our nearest potentially habitable world is a rocky body of roughly Earth's mass, in the correct temperature band, being sterilized on a daily schedule by the star that keeps it warm. That finding does not just concern one planet, and this is why it matters more than it first appears. Red dwarfs are the most common stars in the galaxy. Around 3/4 of all stars are red dwarfs, and they burn so slowly that they will still be shining in hundreds of billions of years, long after every star like the Sun has died. If red dwarf planets are routinely stripped by their own stars, then most of the real estate in the galaxy is ruled out, and so is almost all of the future. There is more in that system than the one world. In 2022, using an instrument called Espresso on the Very Large Telescope, astronomers confirmed Proxima d, a body of only about 1/4 of an Earth mass on a 5-day orbit, detected by a stellar wobble of roughly 40 centimeters per second. That is walking pace, measured across 4 light years. A third candidate, Proxima c, with a period near 5 years, remains unconfirmed and disputed. And in August of 2025, a team using the James Webb Space Telescope published something remarkable about the bright pair next door. In data taken in August of 2024, they found evidence of a candidate planet orbiting Alpha Centauri A, roughly the mass of Saturn, at about twice the Earth-Sun distance, which places it inside the habitable zone of a star almost identical to our own. Follow-up attempts in February and April of 2025 did not recover it. That sounds like a refutation, and it is not. The team simulated millions of possible orbits and found that 52% of the stable ones would have put the planet exactly where the telescope could not have seen it during those 2 windows. So it is a candidate, a gas giant in the habitable zone of the nearest Sun-like star, probably there, not yet confirmed. Now notice what just happened in the last few minutes, because it is the quiet counterweight to everything else in this video. We know the mass of a planet at Proxima Centauri to 2 decimal places. We know its year to 3. We know the size of a body 1/4 of Earth's mass from the way it tugs its star at walking pace. We watched a 7-second flare across 5 wavelength bands and measured how much it would damage an ozone layer. We have a candidate gas giant around the nearest star like the Sun. Nobody went anywhere. Every one of those facts was obtained from inside this solar system by instruments whose combined cost is a rounding error against the price of a single starship over a period of about a decade. The Alpha Centauri system is being explored right now in detail continuously by a species that has never sent anything further than the Oort cloud's inner edge. Hold on to that, because it becomes important shortly. But first we have to deal with the one attempt that was actually made, because in April of 2016, the same year Proxima b was announced, the same year that Flare briefly made the nearest star visible from Earth, a group of people stood on a stage at the top of a skyscraper in New York and told the world that we were going. The atrium at the top of One World Observatory is 100 stories above Lower Manhattan, glass on every side, built on the site where the World Trade Center stood. On the 12th of April 2016, there were chairs laid out in it, and a podium, and a row of people on a stage who between them represented most of what humanity knows about leaving this planet. Yuri Milner is at the podium. Beside him sits Stephen Hawking. Beside Hawking sits Freeman Dyson, who is 92 years old, and who spent the years between 1958 and 1963 designing a starship that ran on nuclear explosions, and who is now sitting on a stage in New York, listening to someone announce a starship for the second time in his life. Mae Jemison, the first black woman to fly in space, is there. Pete Worden, the former director of NASA's Ames Research Center, is there. Anne Druyan, who wrote Cosmos and put the sounds of Earth on the Voyager record, is there. Avi Loeb of Harvard is there. Philip Lubin, whose paper started all of this, is there. And down the row is Zachary Manchester, a robotics researcher in his 20s, who will describe it later as an unreal experience, a young engineer suddenly in a room with people he had regarded as legends. The pledge is $100 million. There is a promotional video narrated by a Hollywood actor. The text released with the announcement reads, "With current rocket propulsion technology, it would take tens or hundreds of millennia to reach our neighbouring star system, Alpha Centauri. The stars, it seems, have set strict bounds on human destiny. Until now. It is, by any measure, the most serious moment in the history of interstellar travel. More money is being committed than has ever been committed to the problem. The scientific credibility in the room is genuine and enormous. 9 years later, there is nothing. No announcements, no multi-institution meetings, no funding." In September of 2025, a journalist named Sarah Scholes published an account in Scientific American, having spent months trying to establish what had actually happened, and found that the scientists who had worked on the project did not themselves know its status. Worden, the executive director, declined an interview but wrote her a line that is worth quoting exactly. "We have put the program on hold and are working to transition portions to others. Then there is the money, and the money is the part that reframes the whole thing. Most of it never existed. Lubin, the physicist whose roadmap was the technical seed of the entire project, and whose name is attached to it in the public mind, received 2 grants across 8 years. One was for $116,000, and one for about $80,000. We got less than $200,000 spread out over 8 years, he said. His own estimate of the total breakthrough spend on the interstellar program is around $4.5 million across roughly 30 contracts. Against the $100 million that was announced, that is under 5%. His summary is unusually direct for a working scientist. Breakthrough contributed less than 5% of the funding in our program in the end, so it was always a little blip along the way. But in the public mind, the entire program was a breakthrough program, and that is simply not true at all. Milner, according to Lubin's recollection of their first meeting, had said he would commit $100 million if outside reviews came back positive. The reviews came back. Unfortunately that, by the way, never came true, Lubin said. There was no $100 million. Now here is the part I find hardest to sit with, and it is not the money. The physics held. Across all 4 problem areas, the sail, the laser, the spacecraft and the communication system, the teams found nothing that was actually forbidden. What they found was scale. At the founding, the group identified around 30 distinct problems that would have to be solved before a probe could be sent anywhere, and 37 separate research groups convened to work on them. They made real progress. Phased laser arrays demonstrated with tens of lasers, a viable sail material identified and fabricated at sub-micron thickness, a functioning chip-scale spacecraft flown and shown to operate as a communicating swarm. And the honest technical verdict, when it came, was a timeline rather than a refusal. Lubin's assessment: I think it's going to take 30 to 50 years of very hard work by a large number of very dedicated people, much like a Manhattan Project on steroids. Kelvin Long, who co-founded Project Icarus and joined Starshot early, put a realistic launch date at 30 or 40 years out rather than the 20 the sponsor had hoped for. That is not a project failing. That is a project succeeding at the difficult first task of finding out how hard the problem is and then losing its funder when it reported the answer. Some of the details have a particular sting. A group at the University of Sydney worked on the problem of keeping the sail stable inside the beam, attended meetings in 2021 and 2022, shared their findings, and never received a single dollar. One of them, the physicist Michael Wheatland, gave an assessment that manages to be dismissive and generous in the same breath. The whole thing always was outrageous. I never believed it. But I think my perspective on things like this is that if you do fundamental research to try to solve a problem in the context of some outrageous scheme like that, then you can do really useful research. Manchester's chip-scale satellites, the leading candidate for the actual spacecraft, had their own arc. He launched about 100 of them in 2014, and a deployment glitch meant they never released. They burned up on re-entry. He tried again in 2019 and successfully deployed 105 at once, demonstrating that they could talk to each other in orbit as a swarm. And then the Federal Communications Commission declined to permit further flights over concerns about space debris, which, as Manchester dryly observed, would not be an issue at all for craft leaving the solar system. Edwin Turner of Princeton, one of the first people involved, offered a different reading of the ending, and it is the one that has stayed with me longest. He reached for medieval cathedrals, buildings that took 200 years to complete, spanning generations of masons who knew they would never see the finished thing. That comparison is usually made as an accusation against the modern world, a complaint that we have lost the capacity for long commitment. Turner does not think that is what it shows. He points out that the technology of arch and vault and finial barely changed over the 2 centuries of a cathedral's construction, so work done in the first decade was still useful in the last. Ours does not behave that way. It's very hard trying to imagine a major technological thing we're working on now for which they could have done anything at all useful 200 years ago, he said. Nothing they could have done would make the slightest difference to us. If he is right, the reason nobody builds the Starship is not that we are worse than the cathedral builders. It is that our tools move too fast for early effort to accumulate, which is, if you look at it squarely, the incentive trap wearing a different coat. It is also not the first time. In the 2010s, DARPA and NASA seeded a research program called 100-Year Starship, whose explicit brief was to work out how to send human beings light years away within the next century. Mae Jemison, who was on that stage in New York, led it. The Tau Zero Foundation was founded to carry interstellar propulsion research forward after NASA's own Advanced Propulsion Program was cancelled. Project Icarus, the modern redesign of Daedalus, has been underway since 2009. Every one of these is real, staffed by competent people, and none of them has sent anything anywhere. When Scholes pressed for a formal account of what happened to Starshot, a spokesperson promised her a report that would be finished around the spring of 2025 and shared with the magazine. It had not appeared by the time the article went to print. Manchester, for his part, refuses to call it a failure, and I think he has a case. Breakthrough changed society's conception of this kind of stuff as a legitimate area of scientific inquiry, he said. Before 2016, interstellar travel was a thing you did not put on a grant application. After it, people worked on sail stability and laser phasing and chip-scale spacecraft and got papers out of it, and that work exists now regardless of what happened to the sponsor. But hold the shape of this next to everything that came before it, because the shape is the point. Not one of the 11 obstacles in this video was a law of physics. The distance is crossable, the energy is available in principle, the vehicles have been designed twice in detail, the sail material exists, the lasers work in the laboratory, the medium is survivable with a shield and a swarm, the braking problem has an elegant solution that costs a century. The closed ecology is hard but not forbidden. The crew size is computable, and the thing that actually stopped the only real attempt in human history was that a wealthy man got interested in something else, and nobody sent an email to say so. Somewhere in northern Chile tonight, on a mountain where the air is thin and dry and almost perfectly still, a telescope mirror is collecting light. Among the photons landing on that surface, a small number left the surface of Proxima Centauri 4 years and 3 months ago, and have been travelling in a straight line ever since. They crossed 40 trillion kilometres. They arrived on schedule, undamaged, carrying an accurate account of the temperature of the star that made them, the composition of its outer layers, the magnetic violence of its surface, and the gravitational tug of at least 2 planets. They made the crossing without fuel, without a shield, without a crew, a budget, a treaty, a laser array, or an institution capable of sustaining interest for longer than a decade. Hold that, because we are about to need it. So, what would actually happen on a journey to Proxima Centauri? I promised you a plain answer, and here it is. They never arrive. Not once, in any complete plan we currently possess, does the thing that departs Earth arrive at Proxima Centauri. And the reason this is worth saying rather than shrugging at is that it is not one obstacle. It is 6, and they have nothing to do with one another. They are not different faces of a single problem that a single breakthrough would remove. They are 6 separate walls, and every route through the maze runs into one of them. The first is speed. The machines we have actually built need 75,000 years, which means the crew, their descendants, their language, their species as currently constituted, are all gone long before the destination. Whoever leaves does not arrive because there is no longer any such person. The second is energy. The ship that would be fast enough costs at minimum a substantial fraction of a planetary civilization's annual output for a single vessel at perfect efficiency, one way. So the fast ship is not built. It cannot arrive because it never exists. The third is braking. The one fast vehicle we can genuinely describe, the laser sail, the paperclip on a beam, reaches Proxima in about 21 years and passes through the entire system in 4 minutes because the engine that launched it is on Earth and there is nothing at the far end to slow it down. It reaches the star. It does not arrive at it. It takes its 4 minutes of data and continues into the galaxy forever. The fourth is time. Make the vessel slow enough to stop and large enough to live in, and you have a generation ship, which does arrive genuinely and properly in orbit with people aboard. They are simply not the people who left. They are their descendants, 40 or 50 generations removed, born inside a machine, speaking a language that has drifted beyond recognition, carrying out a decision they inherited. The ship arrives. The travellers do not. The fifth is identity. Every clever escape route, the frozen embryos, the seeded genome, the digital mind, the self-replicating probe, works by removing the traveller from the journey. Something is delivered. Something is even built at the far end. But the question of whether what steps out is the thing that left has been answered by quietly changing the subject. And the sixth is the one nobody expects, which is that the rational move is always to wait. Wait for the better engine, the cheaper laser, the next administration, the next decade of progress. That argument is available to every generation in turn. It is correct every time it is made, and it has already been made continuously for 60 years. The ship that never launches never arrives either, and that is the only one of the 6 failures we have actually observed, repeatedly, in real time, with names and dates and press conferences. 6 mechanisms. No shared cause. Each one sufficient on its own. That is what is behind those 3 words, and I think it is a genuinely strange thing to have discovered about the universe. Not that the nearest star is unreachable, but that it is unreachable in 6 unrelated ways, and that physics is responsible for only about half of them. Now the turn, because this is not where the video ends. Everything I have just described is a statement about moving mass, specifically about moving a particular arrangement of matter, a hull, a crew, a biosphere, a person, from one star to another, and having it still be that arrangement on arrival. That is the thing the universe appears to have priced out of reach. It is not a statement about the gap itself. The gap is open. It has always been open. Something crosses it constantly in both directions at the maximum speed the universe permits, and has done so without interruption for 4.5 billion years. Everything you learned in this video about Proxima Centauri arrived here that way. The mass of a planet you will never see, measured to 2 decimal places. A stellar wobble of 40 centimeters per second, detected across 4 light years. A star shifting at walking pace, and we caught it. A 7-second flare, timed across 5 wavelength bands simultaneously from the millimeter to the ultraviolet. The rotation of a star nobody has ever seen with the unaided eye except during a 2-minute accident in 2016. A candidate gas giant in the habitable zone of the nearest star like our own. All of it obtained without leaving, by instruments whose total cost would not pay for one stage of Daedalus. Remember what we called that gap at the very beginning, 40 trillion kilometers of nothing. Then, in the middle of this, we found out that the nothing is not nothing, that it holds about 1 hydrogen atom per cubic centimeter, and that at a fifth of light speed those atoms become a particle beam that strips 0.5 millimeter off your spacecraft and forces the sail to hide behind a shield for the entire journey. Both of those things are true, and here is the third one. That same emptiness, the emptiness that destroys the ship, is precisely why the photon arrives intact. Light does not mind 1 atom per cubic centimeter. Light does not accumulate damage or lose reflectivity or need to be repaired by a Warden robot or require anyone to remain interested for 200 years. The gap between the stars is not a wall, and it is not a void. It is a filter. It has always been open, and it lets exactly one kind of traveller through, and that traveller has no mass and does not experience the trip at all. We are already using it, in both directions, whether or not we intended to. The Alpha Centauri system has been receiving our radio leakage for decades. Somewhere out past the heliopause, 5 silent machines are drifting outward, and 2 of them carry a gold-plated record with birdsong and a Bach prelude, and a photograph of a woman eating grapes. And although they are not aimed at anything and will not arrive anywhere, they are out there, going, in the only way a mass can go. It is worth being precise about that leakage, because it is not a metaphor. Every broadcast transmitter humanity has ever operated has spilled some fraction of its power upward, and that spill does not stop at the atmosphere. The strongest of it is now well past 4 light-years out, which means that whatever was on the air in the early 1980s has already washed over the Alpha Centauri system, arrived, and continued on. It is thin, spread across an expanding sphere. It is far too faint for any instrument we could currently build to detect at that range, but it is physically there, and it is the only thing of ours that has actually made the trip. Our first ambassador to another star was not a spacecraft. It was a leak. So, they never arrive. That was the promise of the thumbnail, and I have kept it as honestly as I know how. But sit with the sentence a moment longer, because I do not think it is really a statement about the journey at all. Every failure in this video happens at the same point, the point where somebody has to be the same thing on both ends of the trip. Take that requirement away and the problem dissolves immediately. Information crosses tonight, light crossed before there was anyone here to notice, and a probe with no passengers will very likely cross within the lifetime of someone watching this. The word that is doing all the work in "they never arrive" is not arrive, it is they. And that is a question about us rather than about the distance, about what we would be willing to count as ourselves. Arriving. A species that decided its descendants were sufficient could go tomorrow, in principle. A species that decided a photograph was sufficient has, arguably, already gone. I do not have a resolution for you tonight, and I would not trust one if I did. What I have is the mountain in Chile, and the mirror, and the light landing on it that left an invisible star 4 years and 3 months ago, and the quiet fact that the crossing that defeats every ship we can imagine is, right now, above your head, happening in complete silence and perfect indifference, several trillion times a second. There is one more thread hanging, and I will leave it hanging gently, because it is the kind of thought that is better taken to sleep than argued with. In 2017, an object called Oumuamua passed through our solar system, and in 2019 a comet called Borisov followed it, and both of them came from somewhere else. Things do make the crossing between stars. They just do it slowly, without steering, and without anyone aboard. Which means the question is not whether anything ever arrives here from out there. Things already have. The question is only what was riding on them.